Okay, so we have 4 cases for inconsistent systems. And what that means is planes, or 3 planes that aren't all meeting at the same spot. Yesterday we talked about 3 planes where they all met at the same spot, kind of look like a spine of a book. You can draw it like this, maybe. And they all met here at a line. Or we talked about consistent systems where 3 planes meet and it looks like a corner of a roof almost, just at a point. So they can meet at a line, a point, or there's the possibility that they're all the same system, all 3 of them. Okay? Now, we're going with inconsistent systems. Our first one is where all 3 planes, none of them meet at the same spot. So plane 2 and 3, or sorry, plane 2 and 1 meet at this line here. Plane 2 and 3 meet at this line here. And plane 1 and 3 meet at this line here. All of the lines they meet at are parallel to each other. Okay? But all 3 of them do not meet at the same spot. So this would be considered inconsistent. There isn't one solution to all 3 of these planes meeting. Our second case is when we have 2 parallel planes and they're cutting the other plane in 2 different lines. Okay? So if we look, plane 1 cuts through plane 3 here, and plane 2 cuts through plane 3 there. Again, an inconsistent system because there are 2 different lines where they meet. Our third system is where all 3 of the planes are parallel. And if they're parallel, that means they're never going to meet. Okay? And our other one is when 2 of them are coincident, and then those 2 planes are parallel to the other one. Again, they'll never meet. Okay? So we're going to talk about the 3 and 4 first, then 2, and then 1. Just because 3 and 4 will be the easiest types to recognize. Okay? So what we're going to look for is, we'll go to the next page. This is actually example 6 on 9.4. So inconsistent were parallel planes. Coincident and parallel. I gotta spell this one right. Nuts. There we go. Faster next time. Okay. So, this example is given like this. They have 3 equations here. All of them are equations of planes, so we'll say plane 1 is the equation of x plus y plus z is equal to 5. Plane 2, x plus y plus z is equal to 4. And plane 3 is x plus y plus z is equal to 5. So, remember when we're looking for consistent systems, even when we look for those, we're looking for parallels first. Anything that would be a scalar of the other. Very quickly, just by looking, we can see that plane 1 and plane 3 are the exact same plane. Okay? Which means we're working with a set of planes that are the exact same thing, so they're coincident planes. So if we were to quickly draw that up, we're looking at something like, something like this, where both of those planes are represented by the same equation. Okay, so this is plane 1 and plane 3. And then if we look at the normals of the plane, we'll look at the normal of plane 1 since it represents essentially plane 1 and plane 3. The normal, or the first normal, will be at 1, 1, and 1. And then if we look at the normal for plane 2, the normal is the exact same, which means we have another plane. It's not coincident because our d value, if we were to move it to the other side, is not the same, but it is parallel since the normals are both the same. So again, our third plane would look something like this in comparison. Okay. So plane number 2 is here. And these are parallel systems, so we know these are going to be inconsistent. We're not going to find an answer between them. There's not much we really need to do through that. Okay? Actually, we'll keep going. Another system we could be looking at, this is example 5 in your book. Okay. And this one is two parallel planes that intersect a third plane. So, they've given us this example 5 in your book here. The equations are, our first plane is x minus y plus 2z is equal to negative 1. X minus y plus 2z is equal to 3. And then finally, our third plane is x minus 3y plus z equals 0. Okay? So, in this one here, again, we're looking to see if we have any parallel or coincident systems. Looking at plane 1 and 2, we notice the normals, and we'll write the normals to them because the normals will give us a lot of information about each of them. The normal for plane 1 is 1, negative 1, and 2. The normal for plane 2 is 1, negative 1, and 2. That's supposed to be 2z. Yes. That's supposed to be a z there. And then the normal for plane 3 is 1, negative 3, and 1. So by looking at the normals, we've already discovered that 2 of these planes are parallel to each other. So if they're parallel to each other, there's no way I'm going to find a line or a point where all 3 planes. How do we spell third? Where all 3 of them are going to meet. So again, we have a system that's going to look something like this. We have 2 parallel planes, so we'll call this the first one and this the second one. And there's a third plane cutting through both of them. Now, I may eventually ask you if there's not one consistent system, is there more than one answer, and what are they? If I were to ask you something like that, that means I'd be looking for the line, plane 1, plane 2, and plane 3. That means we'd be looking for the 2 different lines where plane 1 intersects plane 3 and plane 2 intersects plane 3. In which case, you would be working with plane 1 and plane 3 together to find out the line where they intersect, is what we did earlier or yesterday. And you do the same thing over for plane 2 and plane 3, where those 2 intersect, which is again going to be a line. And we'll just kind of put it blue so it looks similar to our colors, okay? But in this one, we know it's going to be inconsistent. So if the question just asks us for where the 2 are going to meet, we know, or sorry, where the 3 are going to meet, we know they're not going to meet. And algebraically, we could represent this. If we take equation 1, x minus y plus 2z equals negative 1. And we take equation 2 and just multiply it by negative 1. So we have negative x plus y minus 2z is equal to negative 3. And we add the systems together. We're going to end up with 0x plus 0y plus 0z is equal to negative 4. And we know there are no values for x, y, and z, that when we multiply them by 0, we'll get negative 4. So this is a system that cannot happen. We can't have all 3 of them meet in one same place.